Okay, thank you, Alex. Can everyone hear me? Oh, okay, perfect. Yes, so sorry for the really rather vague title. At the time, I didn't really know what I was going to present. So what I'm actually going to talk about today specifically is the reactions of atomic carbon. And so this is a brief outline of the talk. I'm going to talk about why we want to study atomic carbon atom reactions. And I'm going to say a little bit about how we measure the rate constant product yields. That's been said a little bit already this morning in the last talk, so I can go rather quickly through that. Now, then I'm also going to talk about how we use theory to help us interpret these results. That's a very important part of this work. And then I'm going to go on to talk about several example systems, such as those of the reactions between carbon atoms and oxygen-bearing complex organic molecules, and carbon atoms with nitrogen-bearing complex organic molecules. And then if there's a little bit of time left at the end, and I should think there wouldn't be, I can talk about a little bit of extra or recent work on C2N radical reactions. Okay, so why are we interested in reactive atoms in the interstellar medium? Well, so here I've got plotted a figure of various abundances of reactive atoms and radical molecules in the interstellar medium. And so what we can see is, because, of course, dense clouds evolve from diffuse ones, we have very, very high abundances of the atomic radicals. On the pointer. Okay. These very early and intermediate times, which eventually deplete away as these atoms react and deplete onto interstellar ice grains. So with abundances of 10 to the minus 3 to 10 to the minus 5 with respect to hydrogen, the reactions of these radicals are going to have, or could eventually have, a very important influence on the interstellar chemistry. So even at longer times, in fact, we can see that some of these atoms actually remain very high, have very high abundances, so they could even play a role at even longer times. Hydrogen, of course, is a special case. This is always generated. Okay, so but what in fact do these atoms do? What role do they play? And what reactions do they participate in? Now, atomic oxygen is well known to be reactive really only with unsaturated species, okay? So it doesn't react with saturated stable molecules, and it reacts with radicals, of course. So here we can see that oxygen is reacting with propene, and it's forming some fragments. In fact, it's fragmenting this molecule into smaller pieces, okay? This is not leading to increased molecular complexity. Similar case with the oxygen plus C2H reaction. Here we're getting CO formed, and so oxygen atom reactions generally tend to lead to a CC bond fission and lower complexity in the interstellar medium. Now, the case is somewhat different with atomic nitrogen and hydrogen because, of course, these two are completely unreactive with stable molecules. And so really their chemistry here evolves around reacting with radical species. And of course, they can go in both directions. So here we measure the N plus C2N reaction to form 2CN. So this is breaking up the C2N molecule. N plus CH3 forms a more complex molecule. And H plus CH, well, actually forms just atomic carbon. So, but what does atomic carbon do? Well, atomic carbon actually reacts with most molecules. It won't react with CH4 or C2H6, so it won't react with saturated hydrocarbons, but it reacts with unsaturated hydrocarbons, and we can see it inserts into the CC bond and actually forms a longer carbon chain. Similarly, with C2H4, we get the formation of propargyl, and it reacts also with fully saturated molecules such as NH3, and this is work we did in 2015, and we found that it forms H2CN and HCNH. So C-atom radicals, if they react rapidly with a range of molecules in the interstellar medium, could be very important because it reacts with not only radicals, it reacts with a wide range of stable molecules as well. And so it generally leads to increased chain lengths in the studies that we've done so far. So in general, what we see is that C plus HX goes to give CX plus H. So from an experimental perspective, if we see the formation of hydrogen atoms, this could be a good indication of an increase in the complexity. Okay, so what we want to do now is to look at the reactions of atomic carbon with other types of molecules that are present, notably complex organic molecules, to see what they're going to give in the interstellar medium. So how do we do that? Of course, we're going to use the crazy technique, so cinétique de réaction en écoulement supersonique uniforme. This involves the use of a long nozzle to produce a supersonic flow, which produces a flow of argon, helium, nitrogen, with a constant density, velocity, and temperature profile for several tens of centimeters. which corresponds to several hundreds of microseconds. So this gives us an ideal environment to study the kinetics of fast reactions at low temperatures. Now, why use this method and not just simply cool down a reactor where we flow a cryogenic fluid around the walls of the reactor? Well, of course, in this situation, if you're trying to study the reaction of atomic carbon with COMs, for example, such as methanol, the methanol is just simply going to stick to the walls of the reaction vessel at very low temperatures. So in fact, you simply can't study these reactions under simple cryogenically cooled cells. So that's really the major advantage of this technique, and it's really the only one that we can use these days to study the kinetics of these types of reactions at very low temperatures. Okay, so in Bordeaux, what we do is we have the Laval nozzle mounted on a piston which slides inside and out of our reactor. We inject a certain precursor molecule. So for atomic carbon, we use carbon tetrabromide, and by magic, we align the laser beam along the supersonic flow, and we break all 4 CBr bonds at the same time, and we leave carbon atoms on their own in the supersonic flow. Okay, so at the same time, we also inject our co-reagent species in an excess concentration in the flow, so whatever that might be, and we can probe the disappearance of our atomic carbon by vacuum ultraviolet laser-induced fluorescence at 116 nanometers. We can also look at the formation of atomic hydrogen, and this is at around 121 nanometers at the same time if we want to do product studies. So this is just a slide to give you the general methodology, how we actually go about doing the measurements, and it's very similar to what was already discussed a little bit this morning. So we look at the disappearance of atomic carbon in the presence of an excess of our co-reagent species. So the first thing we do is we add a certain quantity of NH3 in this case into the reactor, and we follow the disappearance of atomic carbon. We fit to this profile to get the pseudo first order rate constant, so an exponential fit, which gives us the pseudo first order rate constant. We then change the NH3 concentration and we do the measurement again. We see it goes faster, and this gives us the pseudo first order rate constant at a different concentration. We plot those as a function of the NH3 concentration to extract the rate constant at a given temperature, and then we change the temperature and we do the same thing again. So we build up a series of straight lines like this, and the slope gives us the second order rate constant, which is what we use in the astrochemical models. So here I plot them as a function of temperature, and so for the C plus NH3 case, we see that the rate constants increase as we decrease the temperature. Now, as I said just before, we can also measure H atom yields from these reactions. That's very interesting to get at some information on what the products are of these processes. The way we do that is we switch over to 121 nanometers. We measure the production of H atoms from the C plus NH3 reaction. So here in the blue points. Then we switch off the NH3 and we add in a concentration of C2H4. Because what we know is that this is our reference reaction. We have to calibrate the H atom concentration or the intensity. And so we know that C plus C2H4 produces C3H3 plus H at 100%. So that means in this particular case, because the C plus NH3 reaction also produces H atoms with a similar intensity, it produces H atoms around about 100%, with a yield of 100%. Okay, so that really begs the question, why detect the atomic hydrogen and not the molecular co-product directly? Well, the molecular co-product is obviously much better to do it this way because it's a direct method. And of course, we can see exactly what's being formed. There's no question of the isomers in this case. The problem is, and there are several techniques that allow us to do it, and there are groups working on this right now, implementing infrared and vibrational rotational spectroscopy to study these the formation of molecules. The problem is that you form the molecules with a certain amount of energy. And this is one of the problems. And of course, as you form your molecule, it can be distributed over a wide range of internal states. And so this is going to hamper your measurement of quantitative yields, in fact. So this has actually been done in recent studies, but this is a recent paper by the Wren group, in fact, where they were looking at this single channel reaction. So the only products are HC3N plus H. And they managed to detect it, HC3N, but it was very difficult to put quantitative values on this. In fact, you should get 100% going to HC3N. And I think from what I understand of this paper was that it was difficult to get back this 100% formation of HC3N simply because you're forming your HC3N in a very wide range of internal states. So to sum all those up is very difficult. It's an extremely tough measurement. Now, the advantages of looking at the atomic co-product is, of course, you don't have any internal structure. So you can detect it by LIF, and you've got no rotational or vibrational structure, so you can get a quantitative measurement much more easily. But, and this is the caveat, it's an indirect method, so we need to have further interpretation. Okay, so we know we're getting H atoms formed, but what else is being formed alongside? We don't know that, and that's where theory comes in, of course. So we're going to use calculations of the reactive potential energy surface to try and determine what the major reaction pathways are for these particular processes. And so we calculate the geometries, the energies of the reagents and intermediates, transition states and products using DFT methods. So here the M062X functional with reasonably sized basis sets. And then if we need to, we can go a little bit further and use CCSDT or approximate CCSDT methods based on these DFT geometries to actually get better energies, particularly in the case where the transition states are close to the entrance level. And of course, this plays a big role in the rate of these reactions. So we can I'll show you here an example. This was calculated by Jean-Christophe Loison, and he also did some of the later calculations as well. So here we see that C plus NH3 forms this complex here, which is really quite stable. And then we go over this lower transition state here to form H2CN plus H and HCNH plus H as the likely major products. But we can't rule out that this fragments further because we're looking at atomic hydrogen and we don't know what the co-products are. Okay, so now I'm going to talk about some example systems, some of the things we've looked at in the past. So this was one of the first studies we did, was the C plus methanol reaction. Here we have a temperature dependence of the rate constant increases as we decrease the temperature. And we see that H atom yields around about 10%. Now, this was one of the first studies we did, so it's not exactly the same method, but it leads to, it's basically the same process. We have a reference reaction compared to the target reaction. And so we get very low yields of around 10%. So when we look at the potential energy surface here, what we think is happening is that the carbon atom is attaching to the oxygen atom of methanol to form this complex 1, and it's going over this transition state here, which is just below the reagent energy level, and leading to the formation of CH3 plus HCO as the major products, and eventually a little bit of fragmentation of the HCO to form H plus CO. And so that's where this 10% yield comes in. Now, the temperature dependence here is really due to this very high transition state here. So this is really what gives it this increase as the temperature decreases. And so when we add this reaction into the model, okay, so at early and intermediate times, what we see is we have a huge decrease in the methanol abundance at short to intermediate times, so about 2 orders of magnitude. And this reaches the level that we had previously when we're at longer times, simply because there are fewer carbon atoms present in the interstellar medium in the gas phase. And so the abundances are actually in pretty good agreement with those observed in TMC1. So more recently, we've looked at the carbon plus dimethyl ether reaction. Again, we have a temperature dependence, which is due to a high transition state. You might notice that these are positive. I can go and explain this, but I haven't got time right now. So if someone wants to ask the question later, they can. Okay, so this is what we think is responsible for this temperature dependence here. We have very low H atom yields once again of around 10%. So this is really indicative that we're not forming more complex molecules. We're actually breaking down this dimethyl ether into smaller fragments and analyzing the potential energy surface, which is much more complicated now. What we see is we think because of this low energy pathway, here we're forming directly CH3 plus CO as products. Okay, and there could be several other minor pathways giving a few H atoms at the same time. So once again, in the model, when we add this into the model, we see that we get a large decrease at short to intermediate times in the dense interstellar medium, and we return to the same level as previously, of course, at longer times. So now there's already a problem with dimethyl ether in that we underpredict the abundances in TMC1 by a very large margin. So this is about an order of magnitude too little to the model. So there's already a problem with this, and this doesn't really help things either. Now here we also studied carbon plus acetone. Now here we have a different dependence on temperature. Here the rate constants are temperature independent. And we also see something interesting with the H atom yields, in that when we decrease the temperature, we're getting a H atom yield which increases. Okay, so this shows that something slightly different could be happening here. Now, again, the potential energy surface, and this is not all the pathways. There are many more, of course, which are probably less relevant. So we only include the major pathways here. What we think is happening is the major products formed are C3H6 plus CO. Okay, there's a low energy pathway here going directly to these products. And this temperature dependence could be due to the second channel here, where the carbon atom is actually attaching to the hydrogen atom, the CH3 group. And at low temperatures, this could be involved in some of this hydrogen atom production here through this channel here, leading to H plus HCCH, COCH3. So this was the only one we did that had 3 carbon atoms, in fact. So this is telling us that maybe if we go to even larger complex organic molecules, maybe we'll have an effect where we produce even larger molecules, in fact. So all the smaller ones that we've seen so far have led to fragmentation. Okay, so again, once we add this into the model, we see a large decrease in the gas phase abundance from the simulations, and the agreement is reasonable with the observations in this particular case already. So at least for a certain time during the model. Okay, and this is unpublished work, so we haven't got the model for this yet. So here we've looked at the carbon plus acetaldehyde reaction. The rate constants are very fast and temperature independent. Once again, there's a channel which is really very low in energy. And so this is the reason for no temperature dependence. The major products here are CH3CH plus CO, we think. And here we have very low H atom yields, of course, because these are the major products. So, but what we can notice here is that the H atom signal is actually increasing very slightly. It should do something like this. And in fact, it's not doing that. And this is indicative of some secondary chemistry, in fact, which is producing H atoms. And what we think is happening is this CH3CH or another product is reacting again with CH3CHO to produce supplementary hydrogen atoms. So this is really an upper limit. It could be even lower than that. And the final oxygen-bearing complex organic molecule I'm going to talk about is dimethyl ether. Now, I haven't finished the calculations on this, and we haven't got the model. So, but we've measured the rate constants. They're very fast again, independent of temperature. And here the yields are really low. So clearly this process is very much fragmenting your methyl formate molecule probably into CO and other fragments. Okay, so this is kind of a general theme for these. When you're reacting carbon with oxygen-bearing comms, we're getting fragmentation as the major products. Now, when we go to the nitrogen-bearing comms, the situation is somewhat different. So we measured the carbon plus CH3CN reaction. Here we get fast rate constants. So once again, these low transition states are the reason for them being fast and temperature independent. Here we get H atom yields, which are much higher. So around 60–65% when compared to our target reaction, to our reference reaction. And we look at the potential energy surface, and there are these 2 channels here, which are the only ones that are accessible, in fact, for this particular reaction over the triplet potential energy surface. And so this is nice because we're seeing the formation of larger molecules here. So the carbon is inserting into the acetonitrile to form these 2 species here. And the other 30%, well, because there are no other exit channels, in fact, we can't access them over the triplet surface. We think what's happening is there's intersystem crossing to the singlet surface, and we can get the formation of some of these products here. We don't know which ones because we can't probe them. And once again, with the model, we have, when we introduce this reaction, we get a very large decrease in the simulated abundance of CH3CN, which actually takes it further away from the observed values in TMC1. Okay, now this is almost, we're not going to be able to see this, but so this is also in published work, the carbon plus methylamine reaction. This was completed last year with the aid of a master's student who calculated all these intermediates and transition states. Okay, so we have rate constants, once again, which are very fast, temperature independent, due to these low transition states compared with the reagent level. So this is very constant, the function of temperature. Now it's difficult to read, but the major products are likely to be CH3 plus CnH2. And eventually, because we get H atom yields of around about 35%, there could also be some other products being formed, such as CH3 plus HCNH plus HNC plus H, or H plus CH2 CnH2. So we might be getting some formation of slightly larger molecules here as well. So this is quite interesting. Another thing to notice here is that we're actually preferentially forming CnH2 and not, so the isocyano product and not the cyano product. So, okay. So this could mean that this might be one particular reaction which might lead to a preference in the formation of the isocyano product, so HNC or H2NC. Now, this is not exactly a COM, but it was another reaction that we studied with a nitrogen-bearing species, apart from the three others that I've shown so far, N2O. And so, again, with N2O, what we see, of course, we're seeing a temperature dependence to the rate constant. So this increases as we lower the temperature. Again, this transition state here is quite high. So when we pass through this complex, this is really determining the temperature dependence of this reaction. Now, the products here, there are no hydrogen atoms, of course. That's the thing. So we can't really directly determine products from this particular study, but we use a trick, in fact, to determine what the products might be and what the yields could be, because this reaction is going to have either two particular channels. It's either going to form Cn plus NO or CO plus N2. Okay, and then so what we can do is actually we start with the C plus C2H4 reaction in our reactor. We have a certain H atom yield, and then what we'll do is replace some of the C2H4 with N2O, and we will remeasure the H atom yields, which are coming from the C plus C2H4 reaction. Now, why do we do that? Well, the Cn formed in the first reaction here, the C plus N2O, the reaction we want to study, can then go on to react with C2H4 again to form H atoms, okay? And so if this yield is close to 100%, then we should see that the H atom yield will be identical to one without N2O in the system. And that's exactly what we see. In fact, we see the formation of H atoms at equivalent intensities to the one from the C plus C2H4 reaction. And so that means that this is pretty much the unique channel for this reaction. We get no CO plus N2 formation from that. And that's all from me. I'm pretty much out of time, right? So, okay. Okay, so just to summarize, we've measured the reactions of carbon with oxygen-bearing complex organic molecules. What we see is all these reactions are very fast at low temperatures, even if some of them are a little bit slower at room temperature. And the major products are mostly CO and other fragments. And so we find that these reactions actually will lead to a lower complexity in the interstellar medium. For carbon plus nitrogen-bearing comms, CH3CN and CH3NH2, and I guess you can add NH3 to this as well, although it's not a com. These reactions are also very fast at low temperatures, and they have much higher H atom yields, and so this is a good indication that these types of reactions are leading to an increased molecular complexity. Okay, but we really need to go and investigate other systems of this type to really confirm these findings. So, and as a general comment, of course, we're adding in reactions that are consuming interstellar comms, and they're consuming them in rather large quantities. So all of these reactions are going to decrease the com abundances in the interstellar medium, and so it's leading to less good agreement with observations. And so we really need to look at the model and see where the problems here are involved with simulating com abundances. And that's pretty much all I've got to say. Thank you very much for your attention.